Welcome back to our data science course for life sciences. We have been looking at the binomial distribution. The binomial settings is when there's only two possibilities to really consider, like heads or tails or success versus failure. We'll try to deal with more realistic situations today, diving right into the example. The BBC launched the Loneliness Experiment on Valentine's Day of 2018 and had over 55,000 people worldwide respond to their survey. The table below shows the proportion of respondents who said that they feel lonely often. Let's call the 16 to 24 age group young adults. And suppose that in a similar study, we have a sample of 15 young adults. Alright. So if nothing else, recall that we're chugging through this formula that we developed last week, the binomial distribution formula. We need to be able to plug in the correct values for n, p, and k. N will be our sample size, that's the 15 young adults. P, our proportion, is the 39% that reported that they were often lonely. Oh, I should have read the task first. We are going to find a probability that none of the young adults responded as often lonely. So the description is often lonely. And from the table, the young adults that are often lonely are these 39%. 39% of young adults. And from there, we're going to plug in various values for k. So now, find the probability that none of the young adults responded as often lonely. If nothing else, we have a value for n, we have a value for p. That means k is what we need to plug in. From that task, go ahead and spend a few seconds guessing what the value of k will be. And you are correct in saying that k is equal to 0. And we would go through our probability distribution formula as such. From start to finish on this one, if we had 15 of your peers and we asked, are any of you feeling often lonely? The probability that none of them say yes is very small. So now our new task, find a probability that at least one young adult responded as often lonely. Going back here to the Google Docs. I want to phrase this differently. So for the first 10 people, we'll go ahead and remind us how we handle the words at least one. Okay, so thank you for volunteering some of the answers so far. Several people mentioned that at least one inequalities means greater or equal to 1. Albert also mentions the not zero case. So let's think about that. We have a sample of 15 young adults and ask them if they're often lonely. How many of them say yes? Well, one of them could say yes, 2 of them could say yes, 3 of them could say yes, 4 of them could say yes, all the way up to 15. But rather than doing 15 terms or 15 versions of this calculation, remember that our strategy, probability k is greater than or equal to 1, is to take the complement of the probabilities k is 0. Because at least 1 is completely the opposite of the task I had in part A. The complete opposite, that none of the young adults felt lonely often. And then as you can see, the rest of the calculations is simply the complement of what we had in part A, and is the remaining 99 plus %. Now in part C, I'm basically doing a ton of different examples because there are slightly different settings, different wordings. In part C, I'm asking, find a probability that at most one young adult responded as often lonely. The next 10 people get to rephrase that task. How would we handle the calculation for it at most one? All right. We have some good answers here. The maximum number would be one person. It's the opposite of more than one. K would be less than or equal to 1. Renee was actually writing out the correct R code otherwise. Okay. All right. Good job. Let's see how this plays out in the math speak. So you correctly noted that the inequality would be less than or equal to 1. And when you're talking about individual persons with integers, that means the only two numbers we're going to encounter are 0 and 1. Either 0 lonely people or 1 lonely person. This leads to two applications of the binomial distribution formula, but otherwise a straightforward finish to the final answer. So again, as you could see, while the formula itself might look a bit intense, That's going to be a pretty straightforward calculation once you practice it a couple of times in the homework next week. What I'm emphasizing is your ability to read the problem and be able to suss out the subtlety. Which direction does the inequality go? And how it affects the rest of the calculation. There are a couple more variants I want to show you here. Same setup, the loneliness experiment study of 2018. 39% of young adults said that they are often lonely. And let's suppose that we have a sample of 15 of your peers. Find the probability that at most 2 young adults responded as often lonely. So taking up the difficulty a little bit, how do you think we're going to describe or write out the math work with the wording at most 2? Awesome. So as we're proceeding more and more into this session, you're starting to see the patterns. So for example, Yasmin and Mark noted that the inequalities would be less than or equal to 2. And folks like Andrew and Meishan noted that the numbers, the k values would be 0, 1, and 2, amongst other people as well. Good job. Oops. Okay, so like you said, the inequality is k is less than or equal to 2. Which means that we have focus on these 3 k values, 0, 1, and 2. You'll plug those into the binomial distribution formula. And because there are some ugly decimal numbers here, please continue to round decimal numbers to 4 places so that we maintain some accuracy. And then it's not necessarily fun to talk about loneliness, so we'll do just one more example in this setting. We're going to find a probability that at least 2 young adults respond as often lonely. So the last group of people get to explain how to handle that wording, at least 2. Okay, so I thank you for finishing off these quick math questions here. I hope that the little before lecture assignments help jog your memory a bit. And as folks such as Berenice and Yingtian said, at least 2 means greater than or equal to 2. And we could see that Christian explicitly listed out the K values, 2, 3, 4, all the way up to 15. Thank you all. So, and thus, like you said in the Google Doc, we are dealing with the K is greater than or equal to 2 inequality, which here means the K values are 2, 3, 4, all the way up to 15. Now, like folks in chat are saying, are implying, you would not necessarily want to use this binomial distribution formula 14 times. It would be quite tedious that way. So we're going to leverage our knowledge of complements by realizing it's a little faster to compute this the other way. Find the cases of k equals 0 and k equals 1 first. Add those up, and then simply take the 1 minus complement at the end. And let me show you what the rest of the calculations look like. Oops. There we go. And if you reread these notes, note that task 2b was the complement of 1c. And a question in chat is, well, what if the complement does not save you all that much time? We're just kind of getting used to the ideas. Any truly tedious calculation we're going to run through RStudio instead. At which point the calculations would take nanoseconds, at least for a computer. Okay, the next page, caffeinate yourself, just a bit of math theory here. There's a notion called parameters for binomial distributions. That 1 correspond to success and 0 correspond to failure. One trial of a binomial, aka 2-case event, has that probability distribution table, which, to summarize, means that the event has a probability lowercase p of happening, and the complement for the other case is simply 1 minus p. So, for example, if we're talking about loneliness again, the probability for loneliness is p. The probability of not lonely was 1 minus p. Since we have a probability distribution table, we could run through the calculations of expected value, which the notion that we looked at a few sections ago. And it turns out that the expected value in this setting with this table brings us right back to the letter P. And if there happens to be n events that are independent, then the result will be n times p. I'll show this in the next example. You might recall with our work with expected value, we could also apply a few more formulas to find the standard deviation. We calculate the second moment, happens to be the letter P again. We find the variance with the so-called practical formula for variance. And most mathematicians prefer, once they get here to p minus p squared, many mathematicians prefer to factor out p. If there are n independent events, n of something going on, we multiply that previous result by n. And that's our variance. And then finally, standard deviation is the square root of variance. So in other words, if we have a binomial situation, just at its core, two different possibilities. Finding the mean and standard deviation is now going to be very straightforward because the mathematicians quickly derived all the work in between. It's called a mathematical proof. And furthermore, as we build up to more complicated concepts to finish off this semester here in Bio 18, I want us to start thinking about this range rule of thumb. I forget if we mentioned earlier, but about 95% of data falls within 2 standard deviations. And this range rule of thumb follows that same. At this point, I like to, since this is a biology class, take us back to one of the very first examples of these statistical studies. Mendel and his study that led to the field of genetics. Remember, Mendel was a bishop who was growing peas year after year, but he started to write down how many plants grew and whatnot, and he started to notice some patterns. Reading off the example. When Mendel conducted his famous genetics experiments with peas, one sample of offspring consisted of 580 pea plants, I should say. And Mendel theorized that 25% of them would be yellow peas. If Mendel's theory is correct, find the mean and standard deviation for the numbers of yellow peas in such groups of 580 offspring peas. Alright. The numbers I've given so far, 580, 25% yellow. If I asked you, out of 580 plants, how many do you expect to be yellow when they are grown? As the formulas above imply, it follows what you probably just thought of. Simply multiply those two numbers together. N times P, the 580 times 0.25, means that we expect 145 of the plants to be of the yellow variety. And then we could similarly plug and chug into our derived standard deviation formula to get a standard deviation if need be. Or if your math teacher asks you to do so. So what really happened at the time is that the actual results consisted of 152 yellow peas. I'm asking rhetorically at the moment, is that result unusually high? So we need to put some information together. We need to get a sense of what might be, loosely speaking, an okay number, or what might be an unusual amount. We'll utilize this range rule of thumb above, mu minus 2 sigma and mu plus 2 sigma. plug in the numbers, please continue to keep about 4 decimal places, or keep 4 decimal places. And we'll get an interval being 2 numbers, parentheses, comma in between. And the way I'll describe this in a sentence, since the observation of 152 is inside the range rule of thumb interval, the observation 152 yellow peas is not unusual. The 152 was higher than 145 expected, but nevertheless, it's not unusual. Nothing of interest scientifically, really. I'll stop here and see if there are any more questions from the folks in chat. Let's see, charge my phone. Alright, taking us from the very old classic biology example to, in relative time scales, a much newer example, but this might be pretty old for you already. Airline overbooking. On April 9th, 2017, United Airlines faced a public relations catastrophe when a passenger was dragged off a United Express flight 3411. The aircraft was an Embraer 170 type, which holds 66 seats. In the airline industry's tradition of overbooking seats, United sells 70 tickets. If, generally speaking, 90% of airline passengers show up to their flight on time, what is the probability that all 70 passengers appeared? So for many years, airlines would intentionally sell too many tickets. Not every passenger would show up. Most of the passengers that did not show up deserved a refund anyways. So it was in the company's best interest to sell slightly too many tickets. And most of the time, everyone's happy with that. It was just this one time when every passenger showed up, and it turned out that United Airlines needed the seats to move some of their own employees from one city to another, and they started dragging off passengers who were not willing to give up their seats, you know? To break this down for the calculations, our sample size will be the 70 tickets, and the proportion of passengers who show up to the flight, let's say 90%. I grabbed this 90 from a much older article. This number is definitely much higher, realistically speaking. But using those numbers, the probability of every passenger appearing, we plug and chug the k equals 70, because every corresponds to k equals 70 here. And the probability turns out to be a pretty small number. So this was United Airlines' a possible case for United Airlines to say, hey, why are you bothering us? What are the odds of everyone showing up to the airport and we having this situation in the first place. Oops, sorry, my face was in the way. Oh well. Of course, for a slightly realistic calculation, if the aircraft has 66 seats, the probability of overbooking is greater than 66. So we would need to look at the cases 67, 68, 69, and 70 passengers showing up. Now it seems to be a good a time as any to go ahead and bring us back to thinking about doing these calculations in our studio. I probably forgot to mention, I've uploaded these lecture notes and this set of codes to our CAT courses page for our convenience, so that you could practice with these next week. Alright, same setting, 66 seats, 70 tickets sold. What's the probability of overbooking? N is 70. Make my face smaller. N is 70, P is 9.9. If I ask what's the expected number of passengers, we multiply those numbers together, N times P. So we expect 63 passengers to show up. And there are 66 seats. Sounds good so far. For the airline anyways. What is the standard deviation of passengers? Well, I briefly shown you the math derivation of getting a standard deviation formula for this setting. Square root of NP times 1 minus P. And we get a standard deviation of about 2.5 passengers. If I ask you to build a range rule of thumb interval, that's mu plus or minus 2 sigma. Here's the R code to do that. And here we get a range of values. So I could address questions like, is 68 passengers showing up to the flight unusual? How about 69 passengers? Well, because 68 is inside the interval, I, the statistician, would say it's not unusual. Because 69 passengers is outside the interval, I would say that's an unusual amount of passengers to appear to the flight that day. Oops, I typed it twice. And then, going back to the slides real quick. Overbooking is this slightly complicated expression here, plugging in K values 67, 68, 69, and 70. It's a little too tedious to do by hand, so we'll do this one in our studio. Plugging in those K values into our dbinom function, like such. And adding up those probabilities with the sum command. There is a way to also do this with the pbinom command. Me personally, I don't like to always keep track of like which numbers go where, or having to keep track of like, do I plug in 67 or 66? But I'm just showing you that there is a way to get the same answer with the pbinom function. I just find the top way to be intuitively easier to understand. All right, one more example is to make these graphs. I'm going to push us towards some more abstract notions. and these are called the probability mass function and the cumulative mass function. Before I go through this, I'm going to actually be going through this for like the next 2 weeks. So if you do not understand it right away, don't worry about it. We'll have some time to pick it up. Reading off the example. According to internal research, 71% of UC Merced students are first-generation students. We will use this information to visualize probability mass functions and cumulative mass functions for binomial distributions. Suppose that we have a sample of n students. I want us to be able to graph this situation. Sample size is n equals 7. The proportion of first-generation students, 71%, goes here for P. And what's the graph below? We're going to try out all the k values. 0, 1, 2, 3, 4, 5, 6, 7. You'll have this code uploaded to cat courses. You can see that the PMF is built from the d binom function, and the CMF, the cumulative mass function, is built from the p binom function. A little bit of code here to make a graph, and we'll get something that starts to look like a bell curve, but you start to take notice whether or not most of the information is on your right or your left. Way this graph is read off in the context of the word problem, starting on the far left, the probability that out of 7 students, 0 of them are first generation, the probability is virtually 0. This next bar, the probability exactly 1 is a first generation student is virtually 0. The probability exactly 2 of the sample of students is a first generation student is about 2%, and so forth. 9%, 22%, 32%, 26%. And then finally, at the very end, at the far right, the probability that all 7 out of 7 in the sample of students are first-generation students is about 9%. Now, at some point, I want you to later reread these notes and try to figure out how these graphs are connected to each other. The second graph is called a cumulative mass function. And for one thing, you'll notice at the far right, all probabilities add up to 100%. So the question in chat, I believe, is about this first graph. Remember, we have a sample of 7 students. According to this graph, the most likely scenario is that exactly 5 of the students are first-generation students. That corresponds to this highest graph here, the highest bar here. In part B, another sample of 7 students, but consider the setting of students who had parents that went to college, namely the complement of the first generation students. We'll graph the PMF and CMF again. N is still 7. The change this time is that our proportion is the remaining 29%. That is the complement of the 71% earlier. Since n is 7, the k values once again is 0, 1, 2, 3, 4, 5, 6, 7. When you go through these notes, you'll observe that this time around, the probability mass function is flipped from the first one I showed you. More of the information is towards the left. And the cumulative mass function, once again, adds up to 100%, but you'll notice this last graph will add up to 100% a bit faster than the previous example. So again, if you read these notes later, I'll leave these questions to guide your studies. How do the numbers and results relate to each other, and what patterns do you see? Okay, that's going to bring us to the end of this session. Heads up, next week, I think I'm assigning 3 homework assignments. I'll still be mindful, try to keep the assignments relatively short. Keep in mind that you may do all the homework assignments during the discussion section with the guidance of a mean. But yeah, there'll be a bit of homework next week. For one thing, I gotta start us on the semester project as well. More information in the weekend email. But for now, give me a reflection. Let me know how things went. And that will be it for today. Thank you.